All right, some actual data on a study of 2 treatments published in 1986. And in both cases, there were 350 trials or procedures done. And success rates are in my table here. These are my entries of success rates. So A overall was 78% successful, with 273 out of 350. And B was 83% successful, 289 out of 350. Okay. All right. So treatment B looks more effective overall, right? Treatment B looks more effective overall. Looks more effective overall, right? So if we were just looking at success rates for treatment A and treatment B, just quick summary statistics, we would see that these numbers, 78%, 83%. Now, however, when it is broken down by small and large kidney stone sizes, we see something kind of interesting here. In treatment A, we have a 93% success rate there, and a 73% success rate for large. For B, it is 87% successful on small kidneys, and it is 69% successful on large kidneys. And you might just, if you just look at these percentages, and I've only listed the percentages for a reason, but you might look at this and say, well, this doesn't seem like it makes sense. How can A be more effective on both small and large kidneys, but then overall be less effective when you consider both of them? Right? Well, what is missing in the actual just percentages here, right, is what was the original proportion? And for A, in small, it was 81 out of 87. 81 out of 87. For B, it was 234 out of 270. And then we have 192 out of 263 for A. And then for B, the large, 69%, that's 55 out of 80. 55 out of 80. Okay. Let me just scroll down and move my table that I'm going to reference later on out of the way a bit further. So take a look at this, right? A performs better individually. A performs better individually, all right? The reversal of order here in the ratios, A performs better individually in both cases, but when you consider it together, it's lower than treatment B. This reversal of ratios is known as Simpson's paradox. This reversal of order in ratios is known as Simpson's paradox. Simpson's paradox, okay? And in this case, kidney stone size is what is called a confounding variable. Kidney stone size is a confounding variable. You know, normally if we were doing something like this in a lecture in a face-to-face class, I would probably start out with prompting, you know, does anyone have any idea what Simpson's paradox is? Or have any idea what confounding variable is? You know, can you list some examples and that kind of stuff? But, you know, we're just recording a video. Let's just assume we don't know what any of these things are. Confounding variable, it's an outside influence. An outside influence that changes the relationship between independent and dependent variables. An outside influence that changes the relationship between independent. So what the independent variable in this case would be the treatment. Is the patient getting treatment A or treatment B? The independent variable. So in this case, that's the treatment. And the dependent variable, the success rate. Independent changes the relationship between independent and dependent. In this case, that's the success rate variables. Changes the relationship, okay? Without breaking this up, without breaking this down by looking at the kidney stone size variable, it would appear that B is overall more successful, but in fact, B is really the worst treatment in both cases. Very interesting, right? This is very paradoxical. So how does this happen? Okay. How does this happen? How does this happen? How can it be, without looking at the numbers, how can it be someone say A has a 93% success rate and a 73% success rate for small and large? B has just 87, which is worse than A, and 69% success rate, which is also worse than A. But overall, 83% looks better than 78%. Why? How does this happen? How does this happen? Okay. This happens for there's two things here that happen simultaneously that result in this effect. The size of the groups are very different when the confounding variable is included, right? The size of the groups is very different. Very different when you include the confounding variable. When we include kidney stone size. We include stone size. The size of the groups is very different. Let's go back and look at this, right? Look at these. We in the small group, treatment A only got 87, treatment B only got 207 or only got 270. That's a lot. That is a lot. There's a big difference there. And if you look at the large treatment A, that's where the majority of those are. That is 263 trials, 80 trials, just 80 trials for treatment B. The groups are not evenly distributed at all in that sense, even though total it ends up being 350 and 350. Size of the groups is very different when you include stone size. You need that to happen, and the confounding variable has a large effect on the ratios. The confounding variable has a large effect on the ratios. And so what I mean here is when you consider the kidney stone size, the larger the kidney stone, the large kidney stones just by default are it's a more severe condition than small, right? 73%, 69% are both lower than the 93 and 87%. So regardless of treatment A or B, if it is a large kidney stone, you are less likely to have success, period, regardless of treatment usage. Well, it just so happens that most of the trials in A were on the more severe case, right? And that's going to affect that ratio. Let's put this in the notes here just for completeness, right? I would say, to try to be brief, large stones appear to be a more severe condition. Appear to be a more severe condition. Appear to be a more severe condition. Both treatments performing worse. Both treatments performing worse than small stone cases. Than small stone cases, okay? And so this is what happens. When you have these things happen, then you can have Simpson's paradox, right? Where, again, if you just look at the overall trials, you say 83% success rate for B, 78% success rate for treatment A. So in the future, we should just use treatment B. Turns out treatment B is worse. You should be using treatment A. If it's a small or a large, or even if we don't know. Simpson's paradox. This shows up everywhere, not just in medical studies like this, but really anytime both of these conditions are met in 1 and 2, you can have Simpson's paradox, and it can affect policy decisions in all sorts of areas of life, right? Let's just notate that real quick. Shows up everywhere. There's a ton of examples. The Wikipedia page on Simpson's paradox is a very fun read. Shows up everywhere. Everywhere. And it's important to kind of be aware of this and the idea of confounding variables, that this can affect policy decisions. Anywhere. Policy decisions anywhere, because depending again on what you're looking at, you just might be looking at straight percentages of something without it be broken down into any more detail, and you can make a wrong decision. A classic example of this is the 1973 UC Berkeley gender bias lawsuit, right? The 1973 UC Berkeley gender bias case. This is probably the most classic example of Simpson's paradox, okay? UC Berkeley was sued for gender discrimination on applicants. So just take a look at this overall table here first, right? We have 12,763 applicants, so 41% admission. We have male applicants and women applicants. And we saw 44% admission rate for males in general, and just 35% for females. And so there was a lawsuit that said, hey, you are unfairly admitting, you have got gender discrimination. You are biased towards admitting more men than women into your college. This is not okay. All right. It turns out that after you broke up the information by departments, there's many, many more departments. This is the top 1, 2, 3, 4, 5, 6. These are the top 6 largest, I believe, largest departments there. There's something like, there might have been hundreds. You have several departments, 40, 50, 60, a lot of departments. But just looking at the top 6 largest, it turns out that it was actually, if there was any sort of favoritism in applications, in most of these cases, it was actually slightly more favored towards women. So when you break it up by department, let's take a look at what is happening here. Male applicants. So the largest sets of male applicants here, 825 and 560, went into departments A and B. 62% of them were admitted and 63% of them were admitted. In those same departments, 82% of women were admitted and 68% of women were admitted. The difference here being, look at the number of applicants that you have here, okay? So there were a lot of men that applied, and even though they only admitted 60 some odd percent of them, and they admitted, 70 to 80% of women, there's just way more men that are going to be admitted here overall into the college, which is affecting, you've got this number here, and it's going to affect this proportion overall. It's going to affect that overall proportion, all right? What's happening here is the men are applying to, this is overall applicants and overall admissions. These are pretty easy departments to get into if you're applying for a program in departments A and B. However, if you apply to really competitive programs, departments E and F, for example, overall, they have a much lower admission rate. And in bold here, you see this is the second most in frequency for female applicants. Women were applying to more competitive departments. The bulk of the women applicants were in more competitive departments. You see there's a pretty big jump from 35% to 63%. They were applying to more competitive departments, all right, being admitted at relatively similar rates. Okay? And so the case, basically, ended up, it was a case of Simpson's paradox, really, in that there was not gender discrimination. In fact, you can do some corrections for this when you have uneven sizes like this. You can do some corrections in your table to allow for that. And again, there was some statistical significance showing that in some cases, the departments were actually biased towards women applicants versus against. So it's kind of an interesting example there. All right. So this is really all of this. I just want to, we're bringing this up as we move into multivariate analysis, just as a reminder of some common pitfalls. Other factors may be involved when you are looking for things, right? So if we're looking at total, applicants and admissions, and we break it down by gender, and you say, well, is it the fact that someone's a woman or, identifying as a female or a male, is that affecting, your admission rate, right? Kind of like the common phrase, correlation does not imply causation. Just a reminder to be aware, right? Correlation does not imply causation. Correlation does not imply causation. That's a classic important thing, right? Other factors may be involved. Other factors. There are probably other factors. Other factors may be involved, especially when you're just looking at ratios and percentages. Other factors may be involved. Don't place too much stock in correlation alone. Don't place too much stock in correlation alone. Okay, we're gonna get to more on actual correlations with looking at scatter plots and things like that. But again, other factors may be involved, and so it's something to be the big takeaway here is let's not jump to conclusions and make sure that we've considered any and all possible factors before we start jumping to conclusions. Okay, Simpson's paradox, kind of a really interesting thing to look at, and again, it's very prevalent even in today's society. All right, good. That'll do it for this one. We'll see you in future videos.